Okay, so just a few announcements and so on. Yeah, the videos are coming shortly. So I had quite a few requests to put the book itself online, as opposed to, the book is online in the HTML format, but some people prefer to read text straight through. So we thought about it, I talked to David, and we've agreed. And what we've done is I put it on the Connect website. It should be there now. You should be able to see it. It's in the PDF form. I really do ask you, though, do not circulate it or distribute it or copy it in any form whatsoever. It's just for your own personal use. This is to satisfy our publishers. But as long as it's restricted to the class, it's okay. Right? So you should be able to get that. Hand-in had a bug. It seems to be working now. We've got that fixed. If you had a problem, handy in your assignment, which is due Friday. Oh yeah, one other issue. I got an email from Piazza, signed by 9 of you, saying that you'd like to use Piazza instead of Connect for discussions. Now, it's conceivable. However, it's all set up for Connect right now, and it would be kind of awkward to run 2 discussion sites. But I thought I'd just do a quick poll. So maybe red for Connect and blue for Piazza. Get your cards out. You might as well use them. Except I don't have blue here, so we'll make it green. I mean, technically it's a problem with Piazza because we'd have to upload the class list to that as well to make sure it's restricted and so on and so forth. Okay. So any comments, questions? I mean, all the material is going to be in Connect. That's where it's all there now, right? All the assignments and everything else. All your grades are going to have to be there, so you're going to have to check them in Connect anyway. So if you want to check 2 sites, it's conceivable. I looked at Piazza. Piazza's pretty good, for sure. And the university should have gone with it, but they didn't. So are there any comments people want to make before the... And how strong is your preference? I see people double voting and so on. It's not allowed. I get it. Okay, there's clearly a preference for Piazza. I'll take a look at it. It's clearly not a big deal to use Connect for discussion. It's not that bad. I know it's bad, but it's not that bad. Right? And you've used WebC. What's that?
It is that bad, but we have to get used to it for other classes anyway.
You have to get used to Connect anyway? Yeah, I know. You've used WebCT, surely, or Connect in other classes. It's just a threaded discussion group, which I'm sure Piazza does too. But I'll take a look and see how much of a pain in the ass it's going to be to switch just the discussion to Piazza and leave everything else in Connect. It's going to be a problem for you because you have to check both of them, but you may be checking them anyway for other courses. Okay, I just wanted to get that done. And that's it as far as logistics and so on concerned. Are there any other questions? Again, I encourage you to use Connect for now, for sure. If you have any questions about assignment 0 or any general questions about the course. Any other problems, concerns, issues? No? Good. Okay. So we're going to talk about applications of AI today. As usual, I'll do a quick recap from the last lecture. We went over the last slides very quickly at the end of the last lecture. So we're talking about representation and reasoning systems. So you need a representation to describe problems and to describe queries, okay? Or questions or problems to be solved, right? Tasks, whatever. So, and then you need ways of reasoning backwards from a query or forward from the problem, from the task domain description to get solutions to queries. And then you need to interpret those solutions. So basically we're talking about going from a problem to a representation of the problem with a query as well, do some computation, come back to the representation, and then return a solution, which in our case will almost certainly be an action, right? As we said, an agent is nothing if it doesn't act. So the question is, how should an agent act given the current state of its environment and its goals? And how should you represent the environment in order to help the agent to reason effectively? Those are the kinds of issues that you're dealing with in the representational reasoning system. And then we talked about representational dimensions. There are 8 of them that we're going to consider. We talked about uncertainty, deterministic, where you've got perfect knowledge of the situation, and you've got perfect knowledge of what will happen if you do something in that situation. So that means the agent can keep a model of the world in its head and also roll it forward under a plan. In other words, every time you do an action, you can change the world in your head to be the new situation and so on and so forth. So you've got a perfect model in your head of the way the world will be. So you can construct multi-step plans and be sure that when you execute them in the world will actually unroll in the same way that it enrolled in your head when you were imagining it, when you were doing the planning process. It's a key distinction, okay? But you can't do that in stochastic domains where you can't predict exactly the results of any action. So it gives you that static versus sequential distinction. And then we talked about various representation schemes, explicit states versus propositions versus relations. And it's maybe useful to look at an example related to the one we did before. Namely, how do I represent students taking courses in a university? And I've only got 2 students and 2 courses here. And so it's clear that there are 16 possible worlds or possible states that the university could be in, from neither student taking neither course to both students taking both courses. And this shows a state-based representation. There's 16 states are enumerated here. This is the feature-based representation here. And each one corresponds to a proposition. Say we use features and propositions. If a feature is binary, we can use the word proposition to describe it, as in propositional calculus. It's either true or false, right? So here's the proposition. Student 1 takes course 1, T11. That's either true or false, and so on. And we count in binary over the propositions to get the states. Suppose, though, we had a query, does student 2 take course 2? Then think about the difficulty of answering in the state-based representation versus the feature-based representation. Not only is the feature-based representation smaller, it's just 4 features versus 16 states, but in the feature-based representation, we just have to check the truth of this proposition here. It's either true or false. But if it's state-based, we have to find out if we're in any one of the red states where it is true. Right? So, course overview again. We're looking at basically 6 modules in the course: search, CSPs, planning, logic, uncertainty, and decision theory. Question?
Much about the previous slide.
Yeah.
The difference between a proposition and a relation. What's exactly the difference?
Okay, so we use the word proposition to stand for, if you've taken a logic propositional calculus, a proposition is something that's either true or false. Okay? It has no variables in it. It's just a statement which is either true or it's false in a particular world. Okay? Now, for a relation, we used the word relation before to talk about the relation student takes course, right? Which has variables in it, students and courses, right? And has various instantiations as propositions. Okay? So that relation, student course, is the relation between the sets of students and the set of courses. Okay? That's, if you like, it's a first order notion because it has variables in it, like students and courses. Okay? When you ground it to a particular student in a particular course, then you have a proposition, okay, which is either true or false. Does that work? And as I say, we use the word feature. If it's a binary feature, then it corresponds to a proposition. General features can have more than one value, and if they're multi-valued more than 2, we wouldn't call them propositions. Okay, it's very important to get the vocabulary straight here. Thanks for the question. So we've looked at this before. For these 3 different dimensions, these are the attributes of those dimensions that we're looking at. And we gave examples of a robot, how it would have to, in fact, use all these different representations in order to solve different problems, from the simplest to the hardest kind of problems. So it gives you a motivation for why we are studying these particular topics. I mean, this is a very useful problem, getting a delivery robot to work in a real-world environment. These are the kinds of queries that you could ask of a representation in this particular representational framework. Okay? So, then we looked at further representational dimensions of complexity, we call them, because as you go to the more advanced form of each dimension, you get more and more complexity. And we want to keep things as simple as possible. We talked about flat versus hierarchical, knowledge given versus knowledge learned, goals versus complex preferences, single agent versus multi-agent, perfect rationality versus bounded rationality. We talked for flat versus hierarchical. I gave a planning example of going to the airport. You can plan at different levels of detail, right? You could plan at the flight level and just say, you know, I need to go from here to Chicago and Chicago to Cancun or whatever. That's a very coarse level of planning. Then you get down to executing that plan. You need to actually get to the airport. You need to buy a ticket. You need to pay for the ticket. You need to get to the airport. You need to take a cab, blah, blah, blah. So it's very important to if you're dealing with any kind of real-world problem, to be able to plan at these various levels of abstraction. Or say, if you were planning just moving the delivery robot around, you could talk about planning at the level of cities or districts within cities or buildings within districts, rooms within buildings, and so on. And that's the only way you're going to solve the complexity barrier or the combinatorial explosion problem of dealing with these very hard problems, technically very hard problems. For this course, we'll primarily deal with flat representations, but we know that these hierarchical representations are needed for scaling up. Turns out we will actually do this kind of planning example, so we'll be doing hierarchical representations in planning. Learning, I talked about that before. Important thing to note is that no agent starts with nothing. You have to know something in order to learn something. No blank slate, which is what tabula rasa needs. You need some prior knowledge always. And I talked about the kinds of things a delivery robot could learn. It could learn the map of the world it's working in. It could learn the dynamics of slipping on the particular floor that it happens to be on. And that could vary over time. And it would have to adjust it. You know, it's like driving on ice. You have to be very careful when you're driving on ice, as we've discovered recently. And some of your driving might actually be concerned with figuring out how slippery is the surface. You know, so you can do sort of probes into the environment to pick up knowledge, which you will then use in executing the plan. Right? And in learning, this is called exploration versus exploitation. Right? If you may currently think you know everything, in which case you exploit your current knowledge and just go for it. But sometimes it's good to see if I've really got the best knowledge available. You might do some exploration, which doesn't directly lead to getting to a goal, but will give you information which will help you get to a goal safely. Okay? And driving on ice is an example of that, where you might just wiggle the wheels a bit. It doesn't directly get you where you want to go. It'll give you a good idea of how slippery is it, or just touch the anti-lock braking system to see if it kicks in or doesn't. It'll give you some idea of what's happening on the road surface. So those are the courses where you learn that kind of stuff. And we're typically going to talk about goals, which are either some particular state you want to be in, like particular location for the robot, possessing some material, or some proposition is true. You know, like it's on an even numbered floor. I mean, that could be, you know, it could be any number of floors, and we don't know how many there are, but we'll just say an even numbered floor would be okay as a goal state. That's a proposition. So, but in general, agents will have preferences which are really often just scalars, like real numbers over the function over the states you could be in, right? And you have a preference for each state. You can think of goals as being the same thing, except the preference for the goal state is 1, the preference for every other state is 0. Okay? But in general, it would be more subtle than that, and we could use real numbers to determine that. We want to be as happy as possible. That kind of preference function is often called utility function. And utilitarianism is the philosophy, you know, we should all be as happy as possible. But in general, preferences can be complex. Like you might have multi-objectives. You want to keep the patient alive, but you want to minimize the patient's suffering. And they may conflict. You want to minimize the risk of side effects, keep it as cheap as possible, and so on and so forth. The simplest way to combine simple preferences like that is just take a linear combination of these competing objectives. You know, some linear sum of the life expectancy and the suffering, the risk of side effects, and so on. And we know a lot about how to do that, but in general, that'll be a very non-linear combination of these things. Okay? That's the kind of thing we'll be dealing with. And then I talked about single agent versus multi-agent. And primarily we'll be dealing with single agents. Perfect rationality versus bounded rationality. Do you have unlimited time to make decisions? Or is your thinking time part of your cost? So if you want to minimize your total cost, that's your thinking time plus delivery time if you're FedEx, then you can see that there's a trade-off here. The longer you think, it costs you, but you might be able to reduce the cost of the final plan enough to warrant paying that. So you have to reason about your own reasoning in order to do that, right? That's meta-reasoning. So we won't get into a lot of that, but it's what some people do. And we talked about anytime algorithms that always produce an answer, but the longer you let them run, the better the answer. Okay, so that's all review, basically. Quick review. Any questions about any of that? Okay, so let's talk about some more interesting stuff. We'll talk about applications, again, by module. So what's the point of search? Well, you know, if you wanted to build, I don't know, video games for Electronic Arts, you probably need to do search. Right? If you're building an autonomous agent that's competing against me in some maze-playing or war game or whatever, it's going to have to figure out the optimal path from A to B to cut me off or to kill me or whatever, right? Well, you'd use A*, which is one of the algorithms that we'll learn about. And some of that work started out in the 50s with, that's Art Samuel, famous AI guy, who did this work at IBM on an IBM 650. Jonathan Schaefer at Alberta has taken that checkers program so far that in '94 he built the world champion. He beat Arthur Tansley, I think it was. So he was the current world champion. And in fact, in 2007, Jonathan claims that his program is unbeatable. What he means by that is that the checkers is solvable if you look deep enough in the game tree, and he will always find a solution. Okay? I mean, it'll either be a draw. I think it's a draw if he plays black, but it depends on what your rules for termination are in checkers. You know, when you, after so many repeated moves, you cut it off. But essentially, there's it's certainly the case that that program is unbeatable if it's bug-free. It's a big call, right? And then the same work in chess. So Garry Kasparov lost against Deep Blue. This is Deep Blue here. This guy's playing for the computer. That's the computer. That's Garry Kasparov. And he was very arrogant going into this match. He lost. And several philosophers said, you know, computers will never beat humans at chess. It's an unfortunate prediction. Dangerous to make predictions like computers will never do X. So this was quite a heroic piece of work in terms of the hardware. They built even special chess processors, VLSI processors, which would evaluate board positions incredibly quickly. 480 of them and 30 CPUs. This was, you know, way back in '97. They're searching 126 million nodes a second, 30 billion positions per move, and they go very, very deep, but narrowly deep in this, because as you go down in the game tree, it explodes exponentially. So you have to narrow your search into the most likely set of moves using heuristic functions. CSPs, here's a classic example. Again, there's money in Sudokus, just as there's money in search. If you can find good Sudoku puzzles, you can sell them in books and make lots of money. Sell them to online sites. So you know Sudoku rules. Every row, every column, every 3x3 square has to be a permutation of 1 to 9. And you start out with some numbers given, and you have to fill them in. So here the constraints are, you know, every row must be different numbers. Every column must be different numbers. These must all be different. And we know how to solve those pretty quickly. And in fact, you know, you can generate arbitrary Sudokus and then check to see if they're solvable. Not only solvable, in order to sell your puzzle, you have to make sure there's exactly one solution. Right? It has to be unique, a unique solution, which you can also check with techniques that we'll learn. Constraint optimization. This is optimization under side constraints. It's very similar to the constraint satisfaction problem. There's a company called CPLEX, actually, which did integer programming and linear programming. IBM bought it. In fact, CPLEX bought iLog and IBM bought CPLEX. And there's money here, right? Big money. Because these kinds of optimization problems are huge in industry. If you've done any linear, who knows what a linear program is? Seen a linear program? Okay, not very many of you. Okay, a linear program. Let me see, do I have a linear program in my folder here? Yeah, I do. I mean, just to show you roughly what it looks like. So typically what we're trying to do is we've got some features of our problem, some variables that we want to maximize some combination of them. We want to maximize a linear combination. So here's a linear combination of x1 and x2. And I've shown it here as the vector C2, the row vector there times the column vector. This is equal to k in this case. And we want to maximize this k. Right? But we've got some constraints. You have to be on this side of each of these three lines. Okay? So that's what this shows here. This is a matrix. This is a vector. This is a vector. Column vectors. So this just means that I want to be in each side of all three of the lines. I have to be in, this is the feasible area here. And it turns out there's a theorem that the max will actually occur in any one of these vertices. So clearly, if you bring this in, you will find that it'll touch here first. So that's where I would maximize this linear combination of x1 and x2 there. And these just show these inequality constraints there. Okay, so that's what linear programming is about. So that's incredibly useful. These are some of the, so technically, and then an even harder problem is if you require some of the variables to be integers. Okay, typically what you do, if you've got a mixed integer program, a MIP, then you'd relax the integer constraint, just solve the linear program, and then try and get the closest integers. This is NP hard, technically. They're very, very hard. And they're also typically very, very large, like millions of variables. Okay, if you're dealing with transportation logistics, like all these companies are, dealing with coordinating all the FedEx trucks and planes and trains and God knows what else, ships they use. Or even more complicated is supply chain management, where you want to make sure the right part is at the right place at the right time. If you're Apple, manufacturing all over the planet and bringing it together and making sure it gets to stores on time. Before Samsung, you've really got a problem. And typically Oracle and SAP are making large amounts of money by building this kind of software or production planning and optimization, within a factory or between factories. All of these can often be reduced to constraint optimization problems. Planning. Here's a nice example. Deep Space One actually operated autonomously for a while. They put a lot of AI software on this spacecraft, and it had a problem. Okay, it apparently was using an ultraviolet detector which malfunctioned, and it still managed to determine its precise position using stars and asteroids, despite that failure. So it figured out this is a failed sensor, and I shouldn't rely on it. I should rely on these other sensors because of the inconsistencies, and it had to make a course adjustment as a result of that finding the position. and it fired this ion propulsion system to make that adjustment. This is written up in the AI literature. It's a famous case of one of the first times that NASA made a huge mistake way back in sending all those people into space. I mean, it would have been much better to send robots. Okay, just hundreds of billions of dollars wasted on the space station and everything else. But anyway, and they've always been very, very reluctant to use AI and robotic software, and this was the first example of when they actually relied on it to operate a spacecraft and allow it to do that. Logic. So there's another famous AI project, the Psych project. Doug Lennett tried to codify in machine-usable form all of common sense knowledge. It's a fairly modest goal. And he used logic, so obviously you just use syllogisms like every tree is a plant, plants die eventually, therefore every tree dies eventually. Modus ponens, standard syllogism, and propositional. Well, actually, this is in first-order logic. It hasn't been a great success. I think some of the criticisms are a lot of the knowledge was added manually, so they required hundreds, if not thousands, of graduate students to add knowledge to this database. It doesn't scale well, and it was not well empirically evaluated. But this, it's hard to read on this slide, but this is basically an ontology. Okay? Ontology means what exists in the world. Okay, and they're very important in AI. And so at the top is a thing, and then you break down into different kinds of things, living things and non-living things. You can see this in more detail in the slides. But this is large. It's got 1.4 million assertions, 100,000 concepts. And it's been used a lot, mostly by DARPA in the military applications, because they got more money than they know what to do with. Yeah, so we don't know in detail about most of those applications. They're classified. One of the big successes in logic has been formal verification in chips, getting the bugs out of your chip. Intel lost a lot of money when one of its processors turned out to have a bug in the ALU. So they poured lots of money into building hardware verification teams. And hardware verification has been more successful than software verification. But basically, now they can verify large chips and sort of medium-scale programs. And typically the way you do it is encode the requirement, the specification for the program in propositional logic, satisfiability, right, 3CNF, which is just a simple form of a CSP. So all of the work in CSPs is relevant here. Uncertainty, where you have stochastic variables and static, but you have features here. This is a nice example. If I can get this going, I don't know if you've seen Connect. But the Connect camera is an RGBD camera. In other words, it gets red, green, blue, and depth. It gets depth by, so this is Xbox. Ooh, there we go. Oh, okay. You can imagine. Oh, I know one. Doesn't like YouTube offline, that's why. Anyway, these people are jumping around, running this video game. Using Connect, and the problem with, the way the Connect works is it projects an IR pattern onto the scene, and it sees it from a different angle. So this is known as a structured light solution. It doesn't work outdoors, but it works really well inside if you can control the lighting and so on. And if you have two of them, they can interfere. But that way you can act, because you've essentially got two viewpoints. You've got the structured light coming in this way, your camera view this way. You can determine where those intersect from geometry, and that gives you a 3D point. But they're noisy as hell, these things. So you've got a lot of uncertainty in the sensor noise that you have to get rid of, and they can actually, fit 3D bodies, spaces, etc., to the data. Here's another example of uncertainty. This is a very large Bayes net. Okay, medicine was one of the first areas where Bayes nets were developed. The Bayes net, we'll talk about in the course a lot, is a way of representing the joint probability distribution of a large number, perhaps, of random variables in a causal way. Okay, so basically the way to read these things, top to bottom, is this is a cause of these things. This is a cause of these things, and so on. And there are actually numbers attached to each of these arcs that say how much, if this is true, how much is it likely that this is true? If this is false, how much is it likely that this is false or true? Okay? So this Bayes net, which you can learn by looking up the medical literature and so on, is used for diagnosis in the following way. There are diseases up here, and there are symptoms down here, right? And also scattered in the middle. So you can fill in various pieces of data in this net, and you allow the propagation, the inference algorithm to run, and it'll propagate probabilities back to the diseases. Okay, so you're reasoning backwards from symptoms back to causes or diseases. Okay? And this can be done fairly efficiently, and this is a pretty large net, but they come much larger than this with thousands of variables. And they're used routinely in medical diagnosis, especially in teaching doctors how to do diagnosis, because they train against the Bayes net and so on. And this was done by people like Eric Horvitz, Ted Shortliff at Stanford in the 1980s, 1990s, and so on. So, decision theory. Decision support systems. We mentioned sustainability the other day. So, computational sustainability is this new field that's developing. I mean, it's not just AI is involved. Many fields of computer science are involved. But it's all about computational models for sustainability. Like, a lot of the climate models are not very well verified. They're not very well calibrated. There's been a huge, part of the huge backlash against climate change theories is because actually some of this computer science was not very solid. They developed these models in a sort of ad hoc way and pasting together lots of different Fortran code and C code and C++ and Java. You can imagine what kind of mess it was. And so part of it is just standard software engineering, just trying to make sure these models are good models and validating them in proper ways. But you can go much further than that. You can provide decision support systems for the management and allocations of resources, not just modeling the existing system, but actually doing some scenario modeling for sustainability. So for example, suppose you wanted to, I don't know, capture solar energy and tidal energy and wind energy and so on and so forth. These projects are all very expensive, and they all have their own characteristics, right? The sun doesn't shine all the time, wind doesn't blow all the time. Tides move pretty predictably, but they're in the wrong place. They're not where you need the energy. So there's a huge optimization problem of where should you position these various renewable energy sources to optimize, that is, minimize the cost of energy and to minimize the production of greenhouse gases, in particular CO2. Right? So you can phase off carbon sources of energy. And a lot of work is going on in this. It's very satisfying to work in this area, and it's actually very important, and there's money there. A lot of money to be made. And another issue is how do you shave? The basic issue in energy supply is shaving off the peaks, right? An energy system like BC Hydro has to design its system for the max load, the maximum load, which is typically, in peak summer with air conditioning, peak winter, et cetera. And it has to match the domestic load and the industrial load and all the rest of it. If you can do some peak shaving so that the max peaks are moved down into the valley, the same total amount of energy is required, but the maximum power you deliver is reduced, then you radically reduce the capital cost of your system. And one way to do that is to use different green energy sources that have different peaks. Another way is to store the power. Power is hard to store. Batteries are expensive, so there are many other ways, like pumping water uphill, and there's lots of different pump storage, even compressing air in mine shafts, as some people are using now. Lots of different ways of of saving the energy. That's another part of this optimization problem. Another neat problem is the grizzly bear. So planet's getting warmer. The habitats, the niche habitat for most animals is changing. It's changing fairly fast, much faster than evolution can cope with it. So we have to provide ways for a particular endangered species to migrate from one area which is habitable now to a new area which will be habitable in the future. So a really interesting problem is, and they're doing this in the Rockies, both in the US and in Canada, is designing a migration path for grizzly bears. So that the problem is, what's the cheapest way to build a sustainable route for the bears to move north, basically? Given that you have to buy land and it has many other disruptions, you already have, it's not good enough just to provide a park, because they'll get stuck in that park. They have to be corridors. You have to design corridors, right? Similarly, there's another project on bird migration. Birds fly, they land in the Rifle Bird Sanctuary, the Fraser River Delta, et cetera, and then they move on down to California, to Mexico. As that land is being eaten up by industrial and residential uses, which one should we preserve to maximize the survivability of these different bird species? Okay, really neat problems. So it obviously involves working with biologists and zoologists and so on. Or here about urban planning, right? Suppose you were trying to decide, well, should we put a rapid transit route to UBC? Should we put SkyTrain out to UBC? Well, it might cost, $3 billion. That's a significant investment. Maybe we could recapture some of that by looking at real estate development around the stations, which is an incredible bonanza for real estate developers. Instead of letting them have all the money, we capture it as citizens ourselves, right? So how much could you get back from the stations? Maybe you could even fund itself by the increased real estate value at stations and along the route would pay for the route. It's not quite true, but it's not far off true if you look at what happened on the Canada line. So, or how do you zone areas for development? How do you maximize transit use, et cetera, for sustainability? How do you make sure people can live near where they work? What kind of zoning regimes do you want, and so on and so forth. So we've done some work in this area with the land use planners at UBC. Any questions about any of this? Just trying to give you a flavor. This is another cool example. Flying a helicopter upside down. If I can get this one to work. I'm more likely to get this one to work. So this is Andrew Ng's work. Andrew's a famous machine learning guy at Stanford. Actually, he's now with Coursera, and they're sort of developing online courses mostly, but did some beautiful work in reinforcement learning applied to helicopter control. So you have this this radio-controlled helicopter. You want to fly it, do all sorts of maneuvers. This all you can look at. All sorts. I put some other links on. This link is called Chaos, but it's actually under control. It's quite amazing. There's a whole bunch of great videos showing how this thing can be controlled completely autonomously by AI reinforcement learning techniques. Somewhat more practical example is this one. So this is work done by Sebastian Thrun. Actually, most of this robot car stuff was done started in the 80s with Ernst Dickmanns in Germany, but Sebastian's more famous for doing it. He did it at Stanford and then at Google, and now he's got his own course learning company, Udacity. So this thing is loaded with laser rangefinders, GPS systems, cameras, IR, radar, what else? I think that's about it. Maybe sonar even. put everything, they just threw the kitchen sink of sensors onto this car and got it driving by itself. You can look at the YouTube version of that. I put a link to it. But now, of course, I mean, actually just this week, Toyota and Audi are announcing their own self-driving cars, prototypes. These things are street legal in Florida, California, and Nevada. I mean, these are robots. There it is. This is Google's car driving down the freeway. Again, there's lots of great YouTube video of this thing working. So this is from Boston Dynamics, robot. The idea is a pack carrier for carry all the stuff the soldier needs, run behind him. You can look at Big Dog, etc. All sorts of drone stuff. Terence talked about robot soccer. I didn't start RoboCup. I was involved in RoboCup, but we did build the world's first robot soccer players here using cars. So, summary. We'd like the most general agents possible, but to start with, we restrict the scope. So in these other 3, 4, 5 dimensions that we primarily work at this level, not at this level, but you have to be aware of that option. We will cover these. So there's lots of applications. Bring your color cars next time. We'll use them again. Read the search module. We'll start getting into the actual course content on Wednesday. Assignment 0 is due on Friday. Take a look at the book in PDF. We're done.